So, okay, so this is interesting. So, now, now we can ask the following question. Now, this has, for the interval class, we had VC dimension as 2, and then we explicitly tried to figure out, given n points, how many classifiers, how many possible labelings will I have? And then we said that that was the order of n squared, if you remember, right. So, we put those intervals and then moved the intervals from the right and then moved the intervals from left to right, and then we calculated the number of possible labelings, and that was n squared. We also calculated the VC dimension as 2. Here we have calculated the VC dimension of the axis parallel rectangle class as 4. Now, we can also ask how many possible labelings can I get if I give you some set of n points in this in R2, right. So, basically I give you some points, let us say I give you 100 points or let us say 50 points in R2, and I am asking, hey, you have this class of axis parallel rectangles, take every rectangle, try to label it. Though there are infinite rectangles, I know that I know that there are only finite set of possibilities. Is it going to be 2 power 50 or is it going to be smaller? Now, I know that the VC dimension is 4, and how does the VC dimension relate to the number of possible labelings, right. So, that is the key question we are asking. And the beautiful thing is that, I mean, this is why this theory is so dependent on VC dimension, and it's such a powerful combinatorial object. The key result is that for any data set S, let us say x1 to xn, n can be however big, if the VC dimension of H, let us call this VC of H, equals D, and D is less than infinity, right. So, which is like a finite number. We saw that for the set of all possible classifiers, VC dimension is infinity. Let us say this is not that case, this is some interesting class. Then the number of labelings of S using classifiers in H is at most, and this is the interesting part, n power t. So, let us take a moment to understand what this is. This is saying that I can give you any number of data points. Now, if you have a hypothesis class whose VC dimension you have figured it out as D, which is some finite number which is not infinity, then if you want to figure out how many possible labelings I will get using classifiers in this hypothesis class on the data set that I gave you, then it is not 2 power n, it is at most n power d, which means that VC dimension is making a structural restriction, right. So, there is a restriction on the possible number of labelings the moment I restrict the VC dimension of my hypothesis class. For example, if my hypothesis class was the interval hypothesis class, I could have just done the player thing and then figured out that VC dimension is 2, and even without our explicit argument that it has n squared. Now, this is kind of telling me that you cannot get more than n power d labelings, but remember what was d for the interval class, it was just 2, right. So, VC dimension was 2. So, this is already telling me that you can at most have n squared labelings for any set of n data points, right. Which means the only thing that you will have to figure out to find out number of labelings is you do not have to work out how many number of labelings, as long as you can work out the VC dimension, which is sometimes much easier to work out than the number of labelings. This is telling me that moment I work out the VC dimension and know that it is d, then that implies that the number of labelings is at most n to the d, right. So, and why is this useful? This is useful because in other words, and this is the final punchline, in other words, VC dimension of H less than infinity implies uniform convergence. holds. That is because the probability that RS of HS, the training error of my hypothesis, and the test error of my hypothesis greater than or equal to epsilon is going to be less than or equal to, let us say the VC dimension is d, which is less than infinity, is n power d e power minus 2n epsilon squared. Alright, so this guy, polynomial growth, whereas this exponential decay, and so polynomial growth is much slower than exponential decay, and so this goes to 0 as n goes to infinity, which means that if I get more and more samples and if I am learning from a hypothesis class with finite VC dimension, then my algorithm will generalize, right. So, that's what this is essentially saying, right. So, that's a major result. Of course, there is much more implication of the VC dimension. We are only seeing one directional implication. VC dimension means uniform convergence or learning is possible. In fact, the other way is also true, but I'll not really talk about that in this course. That is, again, I leave that for a full-fledged statistical learning theory course, right. So, but then here the idea was to, talk to you about this important quantity, right. So, and it's super important because it determines whether our training error is a good enough indicator of what the test error could be, right. So, that's and we can figure that out using a single number, right. So, which is the VC dimension, which is an amazing thing. That's point number 1.